Welcome to the Chemistry, Biology, and Math Revision Hub. Today we are doing the Pearson Edexcel International A level, Chemistry Unit 5 for June 2022. This is the part 1 video of this paper. I will do 2 more videos and put their links in the description box below the video. So let's begin with question 1. It says, this question is about catalysts. Some standard electrode potentials are shown below. Here they've given us a table of electrode potentials, and then they continue to ask which of these ions is most likely to catalyze the reaction between peroxide sulfate as well as iodide. Now we need to see that peroxide sulfate is negatively charged and iodide is negatively charged, so they will kind of repel each other, and the reaction, if it occurs, it's going to be slow. That is why we need to use a catalyst. Now in this case, we can know that this is the peroxide sulfate as a reactant, therefore this reaction should be going in that direction. And here we can see iodide. Since it's a reactant, it means that reaction should be going in that direction. So we need to find a suitable catalyst that can allow for this reaction to go forward while the other reaction goes backward. And that means the suitable catalyst should have an electrode potential higher than that, and it should have an electrode potential lower than that. That leaves only these two as possible catalysts. However, because chloride is negative, yet the other two reactants are also negative, it means chloride is ruled out as a catalyst because it will not cause any change. They will be only repulsion. This leaves with only iron 2+ as the possible catalyst for this reaction. Its electrode potential is suitable enough, lower than this electrode potential, yet it's higher than that electrode potential to allow this equation to go that way while this reaction is going on to the other side. And then the ion 3 formed allow that to go to the other direction when this goes to the other side. So let me write the equation that will occur. Peroxide sulfate here will react with iron 2+, producing 2SO4, 2- plus Fe, 3+. This is the oxidized version of the catalyst. And then in the next step, the oxidized version of the catalyst will react with the second reactant, which is iodide, producing iodine plus the reformed catalyst, which is iron 2. So in the end, we will have iron 2. We will have our two products as intended. The catalyst will be unchanged. So the only possible answer here is iron 2. The next question says, which term best describes the type of catalyst for this reaction? Remember, peroxide sulfate is an ion, iodide is an ion, and the catalyst uses an ion, so this is going to be a homogeneous catalyst because they are in the same phase as the other reactants. Moving on, they say which substance is manufactured in a process involving a reaction catalyzed by vanadium 5 oxide. This is easy. It is sulfuric acid. In the formation of sulfuric acid, we begin by production of SO3, and this reaction goes on like this. Sulfur dioxide is reacted with vanadium 5 oxide, producing sulfur trioxide and vanadium 4 oxide. And then the vanadium 4 oxide reacts with oxygen in the air to be oxidized back to vanadium 5 oxide, and that is how this reaction occurs. These are the steps for the reaction, and the real equation should be sulfur dioxide reacts with a half oxygen to produce sulfur trioxide. So this is the equation that should go on, but it's broken down into 2 steps. In one, sulfur trioxide reacts with vanadium 5 oxide, which is the catalyst, to be converted to sulfur trioxide, and the reduced version of the catalyst, then that version is reoxidized to vanadium 5. The answer should be sulfuric acid, because in the production of sulfuric acid, we begin by production of sulfur trioxide. So that is the answer. Question 2 says, this question is about alkaline hydrogen-oxygen fuel cells. What is the half equation at the negative electrode? This is really easy. In here at the negative electrode, there is going to be OH-. So this equation here is out, that is out, that is out. The only possible answer is hydrogen, as well as hydroxide producing water, as well as 2 electrons on the other side. So it should be an A. Part B says, which statement is correct for an alkaline hydrogen-oxygen fuel cell when compared with acidic hydrogen-oxygen fuel cell? Now, this part here is not in the textbook, and I would think if a student was not sure how to answer this, you can use elimination. We know that for alkaline fuel cells as well, or alkaline hydrogen-oxygen as well as acidic hydrogen-oxygen have the same overall equation. Therefore, they will have the same E theta They will have the same DS total and the Kc will not be different. So it only leaves this one here. The catalyst is going to be more efficient. And the reason for this is it can also allow the use of cheaper catalysts, because when they use alkaline conditions, reactions that are going to occur are going to be more efficient, or it will be more easy to manage or more easy to carry out in comparison to when it's just acidic. Question 3. Excess aqueous sodium thiosulfate is added to an aqueous solution of ammonium vanadate 5. What color is the mixture when the reaction is complete? They want us to refer to page 10 of the data booklet. So, of course, I went to that page 10 and I listed the equations that I found. Remember this equation, the reaction is between vanadium 5 and thiosulfate. So if the reaction is between those two, let me get a different color. It means this equation should be going in that direction and this equation should be going in that direction. And based on the electrode potentials we have here, we can see it makes sense. This going to that direction because this is higher than that one. There is a possibility that this reaction is feasible. So what I did to determine feasibility, I calculated the E theta for the cell, which is 1.00 minus 0.09, giving us a positive 0.91 volts. And because the E theta for this cell is positive, we can know that vanadium 5 is going to be reduced to vanadium 4, and that reaction will occur. Then I went on, again, remember thiosulfate is going to be oxidized as vanadium is reduced. So how about a change from vanadium 4 to vanadium 3? I listed equation 12, which is the same as above here. That is for thiosulfate. But there is another equation 15 involving vanadium 4 conversion to vanadium 3. So I also looked at the electrode potentials. Here we can see this one is more positive in comparison to that. And therefore, if we determine the E theta, since our aim is to convert this equation to that direction and this to that direction due to the reaction between that and that, this reaction should be feasible if the E theta for the cell is positive. So here I use 0.34 minus 0.09, giving us this positive. One thing we need to know is, you remember they say they use a higher concentration of thiosulfate. I think they use excess thiosulfate. So excess thiosulfate means this reaction is going to be feasible even if it's a smaller positive value, so it will work. That means vanadium 4 is going to be converted to vanadium 3. Now let's try and see if vanadium 3 can go to vanadium 2. I got equation 12 from the data booklet and equation 9. These are from page 10 of the data booklet. This one here is for conversion of vanadium 3 to vanadium 2, and we can see this value here is negative. Remember, this equation should go in that direction and that in that direction. When we carry out the E theta, it's going to be a negative number because you can see this one minus that gives us a negative number, and therefore this is not feasible. Therefore, this reaction will not occur. Vanadium 3 will not be converted to vanadium 2. Therefore, the final oxidation state here should be that of vanadium 3, and we know that vanadium 3 is green. That is why the answer here was a C. The final color is going to be green, or the observed color will be green. So let's move on to question 4. Question 4 says, which transition metal complex is commonly used as a treatment for cancer? This is really easy. Cisplatin. This is in your textbook. We use cisplatin, not transplatin, so the answer should be a C. Cisplatin is used in the treatment of cancer. Question 5 says, which reagent, when added to aqueous sodium dichromate, causes the shift in equilibrium resulting from in the formation of a yellow solution? Now, I wrote for you the equilibrium equation. Let me get a purple color here. This is the equation for that reaction. Now, remember the question is changing from sodium dichromate, which we know is going to be orange in color. So if sodium dichromate is going to be orange, and we know this is the equation for this reaction, this equation here, what do they add to shift equilibrium to the other side? I said adding sodium hydroxide, because when we add sodium hydroxide, you can see it's going to interact with the H+ ions, reacting with it to form water, and that will mean that the reactant concentration, which is water, has been increased. Increasing the concentration of water will cause a further reaction with the dichromate, converting it back to the chromate 6, which leads to a yellow color being observed. So here I wrote addition of OH minus causes this reaction to occur, producing a higher concentration of water, which is a reactant, and then that increase in water shifts equilibrium to the product side, leading to more chromate 6 to be formed, which is going to be yellow in color. I hope you get that, so the answer should be sodium hydroxide. Next, A titer has an uncertainty of 0.32%. The uncertainty of each burette rating is plus or minus 0.05. What is the most likely value for the titer in centimeters cubed? Now you remember here the titer, we do not know the titer, so I say let the titer be x. And when we are finding percentage uncertainty, we always say the value of the measured value has to be the divisor. It has to be the one in the denominator. So since the burette is read twice, we say 2 times the uncertainty in the burette rating, which is plus or minus 0.05, divide by the value or the volume measured by the burette, times 100 will give you the percentage uncertainty, which we have here, or the uncertainty. So here, making x the subject gives you all this. When you use your calculator, you get 31.25, and the answer comes out being a C. The next question says, this question is about polymers. A repeat unit of the polymer PET has the structure shown below. They said, what is the percentage by mass of carbon in the repeat unit? So what I did here, I positioned all the carbons. You can see there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 carbons. The hydrogens are 1 here, 2, 3, 4. We have 5, 6, 7, 8. There are 8, and oxygens are 1, 2, 3, 4. Remember, we are counting whatever is in here because that is the repeat unit. So knowing that everything is like this, and I know each carbon is 12, each hydrogen 1, and each oxygen is 16, I had to get carbon, 10 carbon, so 12 times 10, divide by the total of this, which is going to be 120 divided by 192 times 100, giving me 62.5, and the answer is that. Remember, they asked for percentage by mass of carbon. It means carbon divided by everything times 100 will give you the answer. Question 7b says one of the monomers used to make PET is benzene 1,4-dicarboxylic acid. They have given us the structure here, and then they ask how many peaks are there in the carbon-13 NMR spectrum of benzene 1,4-dicarboxylic acid. So remember, we are looking for the different carbon environments. Since this thing is similar to that, and that is a ring, we can see that this carbon is identical to that carbon. So they are the same. I call them environment 1. And therefore, this carbon is going to be the same as that carbon. That is environment 2. And 1, 2, 3, 4 carbons are the same. That is environment 3. Therefore, we have 3 different carbon-13 environments. The answer should be a B. Moving on, they say the repeat unit of another polymer has the structure shown. So I try to break it down. If you see something like this, and this is out of the bracket, it shows you this is additional polymerization, and there was a carbon-carbon double bond here. So if I remove that and put a carbon-carbon double bond, I get a structure which is similar to this. Breaking it down or simplifying it, it comes out as that. So they say this polymer is formed by, it should be formed by addition polymerization from the same type of monomer. So it's a single type of monomer by an addition reaction or addition polymerization. So the answer to 7C is going to be an A as well. So let's go to question 8. Question 8 says, which ion is formed when a mixture of sodium nitrite, which is that, and dilute hydrochloric acid react with phenyl amine at a temperature of 5 degrees. This is easy. This is phenyl amine, as you can see here. When phenyl amine reacts with sodium nitrite and HCl, nitrous acid is going to be formed in situ. I don't know if you remember that when we react that plus HCl, the major product produced here is going to be nitrous acid, which is required for this equation to be carried out. So here we can see when this occurs at this temperature below 5 degrees, we are going to produce a diazonium salt, as we can see there. So the structure that should be produced is this. Please watch out for this confusion here. The positive should be on the nitrogen that has 4 bonds attached to it. So the answer here should be a D and not this one here. So the answer is D. Moving on to question 9, it says, this question is about Grignard's reagent, 2-methyl propyl magnesium bromide. As you can see, they've given it to us here. So they say this Grignard's reagent can be prepared by refluxing 1-bromo-2-methyl propane with magnesium in a flask containing a dry solvent and anti-bumping granules. Which solvent is used in this preparation? Now remember, you are reacting, in the production of Grignard's reagent, everybody should know we use ether, because if you use aqueous or water is going to react with a product which is Grignard's reagent, and then it will not be there anymore and mess up the whole process you're going to be working with. It's going to break this bond. It will take away that, and that lead to formation of that, which is going to be completely different. It will lead to the formation of an alkane, which was not required. So here, when the next part they ask, why are anti-bumping granules added to the flask? We add anti-bumping granules so that the solvent burn or the boiling is going to be smooth. No matter what, if it's liquids or if it's liquid and there is a solid, the smooth boiling addition of the anti-bumping granules is to promote smooth boiling so that things do not spill over. So the answer here should be a D. Question C says, the structure of 2-methyl-propyl magnesium bromide is shown, which is that here they say, which statement best describes the sequestered carbon atom? So they ask, is it positive and electrophilic? Is it negative, positive and nucleophilic, negative and electrophilic, negative and nucleophilic? So I did some demonstration for you here. You can see, imagine this is the carbon having 2 hydrogens on it, but it's directly attached to magnesium, the other side, and Br. When you look at these two, metals are going to be positively charged, so I gave a partial positive. And here, this is a halogen, of course, it's going to be partially negative. If this is positive, this creates a negatively charged carbon, and that negatively charged carbon is going to act as a nucleophile. So it's going to be negatively charged, and it will act as a nucleophile because it can attack other electron-requiring species, like if there was a water molecule like that, and you know this is partial positive, partial minus, partial positive. This is going to donate electrons to the hydrogen, stealing it away, producing an alkane, like I mentioned earlier, and that will mess up the Granules reagent that will be formed. That is why we never use water. We use ether as a solvent. So in this case, for part C, the answer should be a D. It is negative and it is nucleophilic. Let's move on. So here, question 8D says, which compound reacts with 2-methyl-propyl magnesium bromide to form 4-ethyl-2-methyl-heptane-4-on? Remember, this one here, you have to know, is it a primary alcohol, secondary, or tertiary? Based on the structure we have here, I saw that this is a tertiary alcohol because you can see there is an R group here, there is this R group, and that R group. So this is a tertiary alcohol. If Granules reagent reacts with something leading to formation of a tertiary alcohol, that thing must be a ketone. So meaning this is out, that is out. So it leaves these two ketones. Now, I'm going to break this one back to produce a ketone that could be. Remember, previously this was a carbon-oxygen double bond, so I positioned it here, put that carbon, and then this structure like that, and that like that. When we look at it, we can see 1, 2, 3, 4, 5, 6. It ends up being a hexane. However, we have to look at if it's hexane, which is the carbon-oxygen double bond. Is it carbon 2 or carbon 3? From here, we can see 1, 2, 3. So it's hexane 3 on. Therefore, the answer should be an A, as we can see there. Moving on to question 10, it says, this question is about the amino acid serine. So this is the amino acid they've given us here, and they ask, which ion is most likely to form if serine is dissolved in sodium carbonate solution? Remember, they have said dissolved in sodium carbonate solution. One thing we need to know about sodium carbonate solution is because sodium carbonate is soluble, and if there is water, it is going to produce an alkaline solution, meaning in there we're going to have OH minus. Now, if you put this amino acid in a condition that has OH minus, it means this acidic part is going to lose the hydrogen to the OH minus, producing water, and it will become a carboxylate. I did that explanation here in detail, as you can see here if you can read. So I say sodium carbonate is soluble, so its solution will form an alkaline solution. The carboxylic part will lose H plus, and it will join with the OH to produce water. And then the carboxylic part therefore forms a carboxylate ion, while the NH2 is unchanged. Because remember, OH minus is going to steal away the proton, so there will be nothing happening to the NH2. The NH2 will not receive the proton, therefore it will remain unchanged. So that is why this is unchanged. This one lost the hydrogen. The answer is supposed to be a D. So I think you can understand that. Moving on to the next part. Here we have, they say serine has a melting temperature in the region of 200 to 300 degrees Celsius. This high melting temperature is mainly due to the formation of Now, this is an amino acid, and you know amino acids are going to be simple molecules, therefore they have simple intermolecular forces of attraction. However, having a very high temperature like this, and it's a melting temperature, means there are stronger forces of attraction than the intermolecular forces. And since these are amino acids, we can assume they can have ionic bonding in between them. So I say the answer should be B, because it's ionic bonds that can cause that very high melting temperature. Okay, so moving on here, which is question 11, and the last part of this video, which is correct for the reaction of bromine with phenol when compared to benzene. Now, I want to show something here. If we have benzene reacting with bromine, and then we have phenol, here OH, reacting with bromine, one thing we need to know is phenol here, OH, the OH is electron donating, meaning the electron density, the electron cloud here is going to be a little bit higher. So we can assume there is going to be a higher electron density. We could assume that. However, the reaction is also going to be more reactive if it's with phenol than with benzene. Therefore, the answer should be A because it satisfies both things. So A should be the answer. So this brings us to the end of this part of the video. Thank you so much for being with us. And please do not forget to subscribe. I'll see you in the next video. Bye-bye.